Yeah, great. So this is a continuation of series of several talks we had on plate tectonics by Ken Condi, and then more recently by Bob Stern and Taras Jerry. So we expect it will generate as much or even more discussion. So we will try to accommodate all your questions in chat or in person, but please stick around. It might take time, but we will get to your questions. And so probably will be enough time for discussion at the end. So with this, it's a pleasure to introduce Jean Bédard and Lyal Harris. Jean did his undergraduate and graduate in Montreal, working first with Andrew Hines and then with John Ladden and Don Francis. And then he followed with postdoc at University of Cambridge in UK, working on modeling as well as a Phanerozoic example of magmatic provinces. And his interest in using geochemistry of magmatic system to infer about early evolution of our planet. And Lyal Harris, originally from Australia, he did his undergraduate at the University of Western Australia and then followed with master and PhD in France, returned back to University of Western Australia until 2004, when he left to Institut National de Recherche Scientifique in Quebec City, where he is based now. And his expertise in using structural geology, geophysics to address early evolution of plate tectonics. With this, I pass it to Jean Bédard. Jean, it's all yours.
Oh, okay, sorry. I can barely hear you. I hope you can hear me. Thanks for coming. Special thanks to Alex for organizing all this. Like I said to him earlier, I owe you a beer. Okay, so we all agree that plate tectonics has been active since about 1 billion years ago, but there's no consensus at all on when it started. There's a significant proportion of the community that believes that the Hadean and the Archean were plate tectonic environments, and the Earth was a plate tectonic planet in those periods. So in this talk, in the first part of the talk, I'm going to present data mostly from the superior craton that I think falsifies the Archean plate tectonic hypothesis. In the second part of the talk, I'm going to propose an alternate mantle overturn driven model to explain the principal observations. And throughout, I'll be pointing out places where this hypothesis could be tested. And in the last 10 minutes, I'll extrapolate the implications of that mantle overturn model for the Proterozoic and discuss a speculative hypothesis for why it took so long. So the Archean, we've known for a long time that essentially all Archean cratons are dominated by granite greenstone terrains with dome and basin patterns that essentially have no modern equivalent, big domes of granite and pinched synclines of metavolcanics. Most now agree that this is the result of sagduction or partial convective overturn, radial lineations, L-tectonites in the zone of sinking where stuff gets stretched. And if you go a little deeper down, like in the Northeast Superior, all you see is stretched shreds of amphibolite grade metabasalt floating in tonalite. If you move a little higher in the erosion level, like the Abitibi, you have a lot more metavolcanic. So, you know, it's pretty much of a muchness. And unfortunately, the last 20 years have seen a focus on vertical versus horizontal tectonics. It's a complete red herring. There's vertical tectonics everywhere in the Archean, but it has nothing to do with whether or not there was horizontal tectonics or plate tectonics. Now, I spent 20 years looking at ophiolites and arcs and flood basalts and, you know, normal plate tectonic rocks in the Appalachian origin. And around 98, the Quebec government was going to map the whole Northeast Superior at a uniform scale. And I thought it'd be great to dip my toe in the Archean and see how it worked. Now, I had no prejudgment. I was quite happy with how the Archaean plate tectonic hypothesis would apply until I saw the rocks. But these are all plutonic. The metavolcanics are trashed. So I jumped at the chance when François Leclerc proposed to Lyal and myself that we direct his PhD work in the Abitibi Greenstone Belt, which is the world's largest and best preserved and best studied greenstone. And this was done with the Quebec and Ontario government surveys, the GSC, and partners from universities and industry. Now, I don't want to badmouth all the great work that's been done on the Pilbara and Barberton, but these things are tiny. The entire Enverwacht group would be one group of 50 in the Abitibi, right? These terrains are just too small to be for us to put it all pieces together in a coherent way, which is why I decided to focus on the largest, best preserved parts of the record, where hopefully we could say something intelligent about how the rocks formed. Now, a little bit of philosophy. Why do people believe that plate tectonics is reasonable in the Archean? Now, there's a whole bunch of bad reasons, including sloppy terminology and resistance to change, but there are two quite good reasons. The existence of compressional fabrics and probable terrain assembly requires that there be horizontal tectonics, requires that there be some type of convergent margin. The question is plate tectonics the only way to do this? In part 2, I'll explain an alternate way to do it. The other important leg of this hypothesis is that there are calc-alkaline volcanics in the Archean, and the dominant component of the continental crust is TTGs, Archean age tonalite, trondhjemite, granite, diorite complexes. And these two packages are equated with arc magmas by uniformitarians. These things formed in arcs, they compose the root zones of continental arcs, et cetera, et cetera, et cetera. And I would argue this needs to be tested. And in the next segments, I'll show that this is completely wrong. These things bear no resemblance to modern art. So it's important that we have a common language, or else we won't understand one another. So we need a good definition of what plate tectonics is, otherwise we can't test for it. My definition is very simple. It's what we see today. And what we see today is large-scale, long-lived crustal mobilism. Everything moves all the time. Sometimes continents pause, but the oceanic part of the system keeps churning away. Where plates separate, you eventually form seafloor spreading centers where new oceanic lithosphere is created, okay? This can be the result of divergence of continents or be entirely driven by movement of oceanic plates that have nothing to do with continents. When plates converge and both are buoyant, you either form a big collisional origin or an accretionary origin of some type. Where one of the converging plates is markedly denser than the other, today what we get is active oceanic subduction, where the oceanic lithosphere, under its own steam, goes under and creates these huge belts of arc magmatism that uniformitarians equate to the beginning of continental crust. And this is the most testable part of the system because it's the part of the system that gets recorded, right? You don't abduct normal oceanic lithosphere, and paleomag is not yet capable of testing the mobility story in a rigorous way. Now, there's no doubt that there's horizontal compression in the Archean. Well, there's no doubt. I doubted it until I started working with Lyal Harris and other structural geologists in the Southern Superior. Here we see an aeromag map with the granitoids forming these rigid blocks, right? And the soft greenstones in between, well, they form these wonderful fold interference patterns. And the Abitibi is a relatively undeformed Archean terrain, which is why I wanted to work there, because we can actually build up the stratigraphy and say something about it. And the seismic profile across the Western Superior shows an imbricated crustal pattern. So no doubt there's compression. What we have to remember, though, is assuming we define this as the type Archean accretionary origin, it's very different from essentially all Phanerozoic origins. You never see these 1,000-kilometer wide doubly vergent thrust and fold belts. with high pressure core zones. And the reason is quite simple, is that Archean crust was too soft to do this when it came into collision. You'd never form thrust and fold belts because it's too weak. You don't upfault high pressure rocks because the crust is too weak. Instead, when you bring this sort of thing into collision, you form these squishy high temperature origins. Now, this is the terminal stage of such an origin. If you're going to accrete blocks, of course, there will be an intermediate stage where these things are assembled and then they get flattened and start flowing laterally. And now, if you're going to assemble disparate blocks involving subduction, today what you do is you form these very characteristic suture zone assemblages of ophiolites, subduction melanges, and high pressure metamorphic rocks. Bob Stern discussed this a lot a few weeks ago. I'm an ophiolite guy, so I focus a lot on ophiolites. And I think you'll all see that lots of ophiolites after one, hardly any in the Proterozoic, and essentially none in the Archean. Now, ophiolites are not subtle things, right? This is the 7-kilometer thick section of the Bay of Islands Mantle that forms a string of massifs that extend for almost 100 kilometers. That's been through two orogenic pulses. And I've worked on a lot of mangled ophiolites because these things get taken up again. And you got to go a long way before you stop being able to recognize this stuff. I'm not going to harp on this. If people want to ask questions about it later, fine. But essentially, there are no plausible examples of Archean oceanic lithospheric mantle of this type. Sheeted dike complexes can be recognized by competent field geologists. These root down into the gabbro, they root up into the basalts. They're associated with characteristic normal fault structures with high intensity hydrothermal system with lots of epidosite, things that we'll all recognize that we see everywhere in the Phanerozoic, but that we don't see in the Archean at all. It's just not there. Okay, so absence of the characteristic suture zone assemblages that mark the junction points of disparate blocks in the collage, like we see in the dunnage zone of the Appalachians, for example. Now I'll focus on the arcs themselves. They're key because not only are they posited to be the most important contributor to continental crust growth, arcs are also considered to be the principal plate tectonic driving force today. So it's a package deal. What's driving the whole process is this thick column of extremely cold, dense, stiff, suboceanic lithospheric mantle. It provides the main driving force for the entire process, right? And it's two sides of the coin, because that stiff, dense lithospheric mantle is the reason that you can transmit all that tensional stress all the way to the ridge axis, where you have that long-lived weakness that focuses mantle upflow and actually creates the oceanic lithosphere there. With time, as it drifts away from the heat anomaly, hydrothermal exchange with the hydrosphere basically cools the whole plate and thickens the oceanic lithosphere so that after 20 or 30 million years, it becomes negatively buoyant. The water acquired here is expelled here. Blue schists form here and have nothing really to do with mantle temperature. It's just convergence rate. The water that is expelled into a convecting wedge. The reason the wedge is convecting is there's mechanical coupling between the downgoing plate and the asthenosphere that drives this cell, allowing water and partial melt of the downgoing slab to impregnate that hot, fertile mantle, lower its solidus, trigger melting, and form our magmatic arcs. So we're going to test whether or not these arcs are there, because if the arcs aren't there, then the wedge wasn't there. And if the wedge wasn't there, the slab wasn't there. And if the slab wasn't there, right? So it all goes back to, it's a house of cards. And if one part's missing, it all collapses. Our practical example is going to be the Western Superior Tectonic collage. This is a slide from John Percival. I actually agree with the paleogeography here. You assembled these northern blocks early, and at 2720, you had this big northern block and a bunch of trash floating around to the south of it, microcontinents, bits of this and that and the other thing, that were sequentially accreted from north to south to form the Kenora orogeny. Where I disagree with John and the uniformitarians is I don't think these were arcs at all. I think that's just wrong. And these things were not assembled by arc processes. So this fence diagram going from north to south shows the age brackets and the justification for this whole arc-driven accretionary origin model. We have, there are all these little bits of older basement floating around that are interpreted to be microcontinents that are far traveled and were welded to this growing accretionary origin. We see the age spans here, and all these terrains were sort of magmatically active after 2750, with shutdowns at 2720, 2700, 26 something, documenting the sequential north to south collisions. The color code here is John's, and is divided into continental Archaean rocks, these red things that are essentially either TTGs with inherited zircons or isotopic signatures that show they had older basement, or are continental arc volcanic rocks, where there's lots of calc-alkaline facies that sometimes rest directly on that substrate, that older substrate. The dark green are interpreted to be juvenile magmatic rocks. The Abitibi is one of these examples. They're interpreted to be oceanic plateaus of some time, punctuated, as shown by these little yellow lines on the side here, punctuated by multiple arcs that were all active all at the same time. Now, there's many problems with this interpretation that I'll get to. One of the, I think, the first one is that, well, it's kind of complicated, right? All these arcs were all active at the same time, but we have good time constraints. If you plug a very moderate 5 centimeter per year convergence rate into this, you can essay a spastic reconstruction, which gives you this, right? 30 million years of subduction at this rate implies that all these small terrains, they're sometimes a few hundred kilometers in width, traveled multiple thousands of kilometers, with the Minnesota Valley terrain traveling over 17,000 kilometers, so it could come into collision with this bit here. Now, closing all these multiple thousand kilometer ocean basins in exact north-south sequence at 2 to 10 million year intervals seems a little hard to believe, as Maxwell Smart used to say. And when you look at the actual volcanic rock packages that are supposed to be continental arcs, they don't look anything like continental arcs. They're missing the single most important volcanic rock type that you see in modern arcs, andesite. They're just not there. These are the plutonics and volcanic facies from Camber. This is Hawksworth's compilation. That rock type's missing. This is not that, right? If there were continental arcs, as these people posit, well, the subduction factory under continental arcs produces a lot of andesite and basite, high silica, viscous magmas loaded with water because they're above a subduction zone. And these magmas form characteristic volcanotypes, stratovolcanoes, that can grow within 10,000 years, 20,000 feet, right? And so even if everything was underwater, these things would inevitably become emergent and shed huge amounts of debris, huge tooth aprons, mostly andesitic, lahars, airfall tubes, all that sort of thing. This is what continental arcs do, right? Lahars, there was no vegetation in the Archaean. There should have been lahars everywhere. Lahars are actually pretty easy to recognize in the record. I've never seen an Archaean lahar, and I don't think anyone has. Now, why were these continental arc volcanic sequences never sampled, right? Most greenstones in Archaean terrains, including the ones embedded in these TTG masses that are supposed to be arc roots, are completely lacking in these downsag arc volcanic sections. Somehow that's downsagging process sampled all the basalts, but never, ever sampled the andesitic rock. Isn't that odd? The counter argument is they were all eroded. All of them, without exception, which again, I find hard to believe. But let's assume this is correct. Where did all the sediment go, right? They would all have gotten dumped into the water alongside. Now remember that in the terminal stages, just before the Abitibi was welded to the Minnesota Valley terrain and the Opinaka to the north, in principle, it was sandwiched between two continental arcs that would have been shedding all this debris into the water, right? Off Central America, for example, there's kilometer thickness of these tooth turbinites punctuated by airfall deposits They're fairly easily correlatable because of their zircons and mineral compositions that can travel thousands of kilometers and should have been being dumped into the basin that now represents the Abitibi seafloor. Well, they're not there. When you look at the intervals separating the main flood basalt sequences in the Abitibi, extending from 2730 to 2690 something, there's none of this andesitic debris. You have chemical sediments indicating starved basins with no terrigenous input whatsoever. Airfall deposits are actually not that hard to spot, right? They're often graded, and we see them all the time in Phanerozoic terrains, but they're not there. When you do find sandstones, local derivation, mostly basalt and TTG fragments, local fault scarps, TTG domes that poked up out of the water, nothing that resembles far-traveled airfalls or distal andesitic debris. The sedimentary record is essentially inconsistent with the existence of voluminous Archaean arcs of any type. Now, if you take a worst case scenario, which is what most people working in the Archaean have to deal with, you've got a little shred of metabasalt. If you're really lucky, you'll get a way up indicator, and everything's an amphiboloid grade, right? So when you see komatiite and different kinds of basalt and andesite, it makes a certain amount of, it's plausible to suggest a plate tectonic interpretation for this. But when you have a well-studied stratigraphy, and the Abitibi stratigraphy has been under study for 100 years, basically, amazing work by the OGS, MRN, GSC, universities, industry, thousands of kilometers of drill core, age dating with 1,000-year precision, depositional relationships. We know this is a layer cake. It's a little shuffled by the overprinting compression, but it's a layer cake. Everything's deposited on one or the other. And when you see big gabbro sills, well, they're feeding the stuff above it. So it's a layer cake. If you are to apply the knee-jerk identification of magma types and tectonic environments, you're forced to argue that this 50 million year stratigraphy was occupied by at least 5 plumes and 7 arcs. That's a lot. That's an awful lot. And if you focus on these upper members here, the Tisdale arc is supposed to be 2703, the Kinnard-Javis arc is 2701, and the Blake River arc is a couple of million years later. Now, the problem is that the arcs can't be expanded or shrunk at will, right? There's a fixed scale. The stuff is coming out of the mantle because that's the depth that the slab is degassing at. And typically, the arc front, and all the Abitibi calc-alkaline sequences are interpreted to be arc front because they're all extremely proximal, coarse stuff, rhyolite domes, right? You're not looking at distal deposits, you're looking at arc front deposits. And these are typically 100, 150 kilometers away from the trench. So we're asked to believe that there was a robust arc, a big plume arrived to deposit komatiites and flood basalts. You obliterated this arc, you renucleated a new arc, brought it down 100 kilometers, laterally 150 kilometers, to generate the second arc in 2 million years, 7 times in a row. I don't believe it. Turning to the geochemistry, the reason people say there are Archaean arcs based on geochemistry is because there are negative niobium and titanium and all. These data are from the study we did with François Leclerc on the Wakanichi, which is a formation rank calc-alkaline unit in the Abitibi, sandwiched between 2 thick flood basalt sequences that are only weakly contaminated, and is pretty representative. And the low strain allows us to really, do the business on this. So these are pretty typical. So in some ways, in a very superficial way, they look like arc magmas. But unlike most modern arc magmas, they show systematically increasing heavy rare earth depletion and positive strontium and europium anomalies. Now, Julian Pierce published a really neat diagram to help us unravel all of this. The observation is that essentially all modern arc systems, like the Marianas shown here, show arrays at high thorium and terbium that are systematically offset from the oid-moib array that includes all modern morb and oid. The reason morb and oid occupy this array is that partial melting of normal mantle gives us a vector of 1 because the partition coefficients of thorium and niobium are essentially 0. And so the ratio of KDs means there's a slope of 1. The only way you can shift over here is by physically adding thorium and not adding niobium. So when the fluids escape here, they carry the thorium and the light rare earths and the Lyal. They don't carry niobium and titanium. They metasomatize that mantle, and lower its solidus, it melts and gives you that characteristic modern arc signature. Now, if all Archean TTG belts and continents are products of arcs, you would expect them to follow this pattern because that's how arcs work, right? Well, unfortunately, they don't. The overwhelming majority of Archean volcanic rock types define oblique arrays rooted in the morboid array at compositions that are significantly less depleted than morb and extending obliquely up towards a component that looks a lot like TTG. Here I show the field for the Blake River group, same thing. And these are completely different from modern arc suites. So the source-metasomatic process that occurs in the mantle wedge was not occurring in the Archean. The only way to create a spread in this kind of diagram is mixing. The little B to C leg there is 90% gabbro fractionation, diddly squat, right? That A is that extreme rhyodacite from the Wapinichi. And all I did there is mix, uncontaminated basalt with that to form this mixing curve, and the red dashed line is AFC, so a less extreme process. So you can recreate that spread essentially by mixing AFC and mixing. And these are just element ratios, but the mixing works for all trace elements. Here I show the average Bruno basalt, that uncontaminated basalt that came up after the Wapinichi was all over with, mixing with the extreme rhyodacite that looks just like a TTG, and that formed by high pressure melting of a similar basalt in the presence of garnet, which is why there's positive strontium europium anomalies and heavy rare earth depletion. These heavy dashed lines are mixing lines between that uncontaminated Bruno basalt and that extreme rhyodacite. And you can see that about 50% mixing exactly reproduces the pattern of the calc-alkaline andesites that form part of this eruption package that's sandwiched between these very thick flood basalt sequences. So these are conduit hybrids, basically. They have nothing to do with modern arc magnetism. The andesites are mixing in conduits. So you have multiple underplating, you have a thick crust built up by repeated eruptions at the surface with lots of conduits in it. It heats at the base in the presence of garnet to retain the heavy rare earths. You form melts that look like TTGs that eventually aggregate and form diapirs that could erupt to form the type 1-2 dacites that we see in these terrains. You could get uncontaminated basalt erupting. You could get slightly contaminated basalt erupting. You could get basalt that mixes in the conduit system with this calc-alkaline suite to form these very heterogeneous andesites that we see in these very narrow formation rank calc-alkaline units. This is a hot pipe system. It piles up from the top to the bottom. These aggregated melts eventually segregate to form TTGs. When you form a shallow chamber, you form a shadow zone that prevents further eruption of basalt in that area, and you melt the wall rocks to form the characteristic type 3 rhyolites that lack the garnet signature and are spatially associated with VMS deposits because these represent shallow hydrothermal systems. So this has nothing to do with arcs, right? So as scientists, we're supposed to test our hypotheses. And unfortunately, the Archean plate tectonic hypothesis has failed miserably. The fundamental volcanic, metamorphic, sedimentary rock types and the geochemical signatures bear no resemblance to modern arcs. So the hypothesis fails completely. So we need a new paradigm. And in the second part of this talk, I'm going to offer a working hypothesis for an unstable stagnant lid model or episodic mobile lid, depending on how you like your terminology, driven by periodic mantle overturns. Now, I've been slowly putting this model together in my head over the intervening years, and it's gone through multiple stages that you can trace in my publications. What put me onto the overturn story was a very interesting discussion I had with Craig O'Neill on a bus in China while drinking whiskey for breakfast. And he explained the results of a lot of numerical models that indicated that that early planets like Earth and Venus, telluric planets, at the early stages of their history, when they have a chondritic budget of trace elements, go through this periodic overturn behavior. This shows Nusselt number, which is kind of an exotic thing. It's the ratio of convective to conductive heat transfer. Conductive is very low, convective is very high. Look at how big these things are. And the story is that the early Earth has a lot of trouble evacuating its heat. And it goes through these periodic instabilities. At some stage it stops. Earth goes into a mobile lid regime like plate tectonics, and eventually fossilizes into a stable stagnant lid regime. Whereas this is an unstable stagnant lid regime in this terminology. A lot of different model approaches have been used. I list a few of them here. I show some models from Gilman and Tackley, and all these models show pretty much the same thing. Episodic, very large peaks of volcanic and magmatic productivity, separated by interregna with very low activity. And the peaks in magmatic activity correspond to peaks in surface velocity as well, separated by stagnant lid sensu stricto episodes. So this has been referred to as an unstable stagnant lid. And I think it's, like a lot of people, that it's driven by periodic mantle overturns. So I put together a geological model based on what I know that is working forward from these numerical models, building in my prejudices because I'm putting in what I know, and the next step is to back test these against different hypotheses, different inputs. And the idea is that sort of a generic window in the Archaean world, where the Earth alternated between a stagnant sensu stricto lid episode and a mobile lid episode. So a lot to go through here. We have a sort of between overturns, you would have the existing Archaean-Style Oceanic Lithosphere floating around, lacking the very stiff mantle root that modern ophiolites have because the heat flux was too high. With time in the Archaean, that root would grow, making Archaean-Style Oceanic Lithosphere progressively stiffer and thicker. But through most of the Archaean, the numerical models like those of Sleep and the analog models, from Johnson, show that the convection cells in the upper mantle would quickly erode that lithosphere. So most Archaean oceanic lithosphere would be crust-dominated, lack a mantle component, extremely weak. These cells, a lot of debate about their aspect ratios and how that works. But the end result is that between overturns, the upper mantle would cool because of heat loss to the surface and because they have very low radiogenic heating rates. Whereas the lower mantle, which didn't up well and didn't lose its incompatible trace elements, would be slowly heating up, because in addition to the fact that it's gaining heat from the core. So I would call this a stagnant lid sensu stricto stage or a hot pipe stage. With the buildup of heat, eventually this stuff goes buoyant and the mantle would overturn. You get these large upwelling zones. This is purely schematic. It's not based on anything except my gut feeling. This is something that would be very good to explore with numerical modeling methods. I'm going to go over each of these different aspects in turn. I try to emphasize that this is not intermittent subduction or plate tectonics, because there's no subduction zones and there's no spreading ridges. So we're lacking two of the characteristic Archaean Phanerozoic plate tectonic environments, which is why I don't refer to this as intermittent plate tectonics. Okay, so just going to backtrack one here. Let's start by looking at this part of the system where these overturn upwelling zones that I call oozos to differentiate them from plumes, because plumes have a different source, different scale, and different longevity to these oozos. So these overturn upwelling zones come up and deliver a lot of magma and heat to the crust. If they come up under an existing continent, well, it's going to rework that continent, will probably destroy large parts of the subcontinental oceanic lithosphere, freak mantle. And I think the Northeast Superior is sort of like an extreme case of this. This is the age distribution. I mean, over 50% of the rocks are in this 20 million year age window, including all the granites and granodiorites and things. Everything older is tonelite with greenstone. And it got remelted in that time window, as shown by the isotopic signatures and the presence of ubiquitous inherited zircon cores in these rocks. These melt and form these. There's admixture of primitive basalt and there's admixture of older stuff, but most Archaean TTGs in that paroxysmal window are large degree remelts of older TTGs. And so on back to the original turtle, which is metabasalt melting to form TTG. I would argue that the volume and spatial scale of this, and this age distribution is not restricted to the Northeast Superior and is probably common to most Archaean cratons. So essentially the whole surface of the Earth was reactivated in that time window. Looking at the Northeast Superior, here color-coded so that only rocks in that 20 million year age window are shown. That's a lot. And half of the white stuff is granitoids that are only slightly younger, that represent the die-off stage of this pulse. I just want to point to these purple guys. Those are enderbites. They're not metamorphic rocks. They're igneous rocks, plutonic rocks with TTG-like compositions, but phenocrysts of OPX and CPX, and interstitial hornblende and high titanium biotite. These are plutonic rocks. They are injected into amphibolite facies metavolcanics, basalts, forming orthoproxenite reaction rims, and they yield 2-pyroxene and feldspar solvus temperatures over 1,000 degrees. Now that's pretty hot, right? That is essentially the liquidus with moderate water contents of a tonalite. So these things, like the tonalites, came up as largely liquids, very hot. And to generate that volume of partial melt, I argue you need a correspondingly thick volume of magmatic underplate, which I suspect is related to the ascent of an overturn cell. We've argued that the radial structural pattern of the superior records extension and then compression related to ascent of one of these overturn cells under the Northeast Superior. And just want to focus on the Southern Superior, and that this 2780 to 2720 phase records partial disaggregation of an original Superior 1. These are not far-traveled mini cratons. This represents disaggregation of the existing Superior craton that was put together in the previous cycle. Areas of maximum extension create juvenile metavolcanic belts that start at 2750-ish that lack isotopic evidence for older material beneath it. Areas of these older cratons that had the subcontinental lithospheric mantle completely destroyed would be essentially all reworked, like the Northeast Superior. Whereas some areas that have rumps of surviving subcontinental lithospheric mantle would behave more coherently as rafted microcontinents. If you want a modern analog, the Red Sea and the Arabian Gulf, you have upwelling under here. It's moving that way. It's ripping off chunks of continental lithosphere, forming ephemeral oceanic basins. I suspect the Western Superior is recording this on a mega scale. New data from the Quebec sedimentary belt, which represents one edge of this system and grades into the megmatitic Ashwani P complex, Recent proposals by Pleven and others suggest a very similar scenario, with the upwelling stretching the continental lithosphere. There's continentally derived sediments here, a lot of magmatism injected into this, or magmatization, very high thermal gradients. Okay, so we've been looking at this part of the system, but oozos could come up under oceanic lithosphere too. And what they would do then is create that first crop of TTGs and start the process of cratonization. It's repeated upwellings under these progressively cratonized bits that form the continents. Now, the melt coming up in these oozos, I would argue, represent the typical background garden variety Archaean tholeiites that show very weak signs of crustal contamination. And these are the same whether you go from 3.5 to 2.7, and could plausibly represent repeated sampling of that upwelling mantle that is undepleted and looks like primitive mantle in many ways. Viewed isotopically, what's his name? I have a mental blank here. Bill Griffin suggested a lot of these patterns reflect periodic mantle overturns, just as I have here. So the original primitive mantle signature yields basalts that go this way, continental crust that goes that way, and depleted mantle that goes this way. And each time you get an overturn, you reintegrate some of that signature. You mix basalt with the differentiated granitoids and shrink that part of it, and you mix primitive mantle with depleted mantle and shrink that part of the signal. So we can reinterpret part of this secular evolution as repeated influx of churlish basalt into the system, carried by these upwelling oozos that mix with the existing depleted mantle to form hybrids that explain this part of the spectrum. Now, all existing crustal growth paradigms, most of them anyway, assume that depleted mantle was homogeneous. Everything is well mixed, and these are the restites, and anything that doesn't look like this is not juvenile. Whereas this model suggests that all this stuff is juvenile, and this stuff is reworking of the older depleted stuff that otherwise wouldn't melt much. When we get into a plate tectonic world, the plate separation randomly samples the depleted mantle because there's none of this primitive mantle stuff coming up. Now we're going to move to crustal mobilism. Obviously, if this is coming up and this is going down, something in between is going to move sideways, right, to element the flow. We know that the subcontinental lithospheric mantle is of Archean age from various types of dating approaches. And so just like modern continents today, the keel catches in the mantle wind, and that's what's pushing the Americas west. It's not slab pull, it's not plate tectonic driving forces. And we argued in previous publications that this is why Archean continents are able to drift despite the lack of arcs and spreading ridges to supply additional thrust. So I'm going to look at this part of the system now, indirectly by looking at Venus. Lyal downloaded the Magellan dataset and did a structural interpretation of Ishtar Terra, notably Lakshmi Planum here. Lyal will be talking about Venus more next week, but I'm cheating here and summarizing some of these results now. We're pretty confident that there are continents on Venus, thick crusted, low density highlands. And surrounding them on all sides are these orogenic belts. And Lyal did a first order structural analysis, a lot like air photo analysis for us old guys. And you can see these huge linears, faults with drag folds, sense of motion, allowing a first order structural interpretation, showing that everything to the south of Lakshmi Planum is related to rifting. These are, 500-600 kilometers wide. To the north, we'll focus a little bit here. You have sinistral strike slip faults on the left, dextral strike slip faults on the right with a shear sense reversal, and thrust faults mostly in the foreland, which is about 1,000 kilometers wide. The kinematics and scale of this is almost indistinguishable from Indochina being expelled from in front of the Indian indenter. Same scale, same structures, same kinematics. So we argued that Venus has continents that drift intermittently with two phases. The Maxwell Mountains would represent a later collision superimposed on this one. And as it moves, it piles up the background basalt-dominated oceanic lithosphere for Venus to form 1,000-kilometer wide origins with a rather uniform structural pattern. And we argue this is an analog for the Archaean Earth. If you compare it to the Abitibi, for example, these are Lyal's interpretation of the major late strike-slip faulting. You'll note that low gold deposits are all focused on these major transcurrent faults. And what Lyal did was he took the Lakshmi-Planan model, flipped it back to front and changed its direction to match the kinematics of the Abitibi. And when you do that, you see these big dextral and sinistral fault systems that suggest the Abitibi is a terrain being expelled from in front of an indenter, which offers a very interesting insight into how gold is formed. Now, it's always amazed me that Archaean structural interpretations never consider the possibility of indenter tectonics. I mean, these are small terrains. Indenter tectonics should be ubiquitous. So if we interpret the Abitibi as being this part of the system, it initially formed through failed subduction, subcretion, crustal thickening of these oceanic terrains that get cooked up, form chondromite, tonalite, expel metamorphic fluids that are potentially auriferous, but there's nowhere for the fluid to go because the whole system is under intense compression. But when that terrain squirts outside, those major transcurrent faults go from being compressional to transtensional. And suddenly all that fluid can drain to form these auriferous ore deposits, right? And the late Shoshonites have a similar story. If people are curious, I can go over this in the question period. So we posited that Archean continental drift overprinting the stagnant-lid system created what something that looks like modern, Archean accretionary origins. The background is Archaean-style oceanic lithosphere, 30 to 40 kilometers thick, no lithospheric mantle, lots of basalt with occasional tonalites and trondhjemite formed by basal melting. When the continent approaches, this thing goes under compression, it gets under thrust, you form these major reverse faults. I would argue that the Greenlandic cratonic terrains are examples of this. There are long strike equivalents that get imbricated by the overprinting compression, forming rudimentary paired metamorphic belts like those that have been documented in Greenland. The tail end of this thing, though, is dipping in hot mantle, right? It's soft to start with, and it's being heated up. So it drips off. It could drift off as big bits, little bits, but overall be so weak, it won't be able to drag the rest of the plate with it. And this is key. This is how the Archean differs from the Proterozoic and the modern. There's no suboceanic lithospheric mantle to stiffen the oceanic slab and allow it to drag everything else behind it. It drips off. Now, there's an element of rotation here, allowing localized upwelling of mantle between some of these slivers that could allow decompression melting in the presence of fluids being expelled from these downgoing blobs, locally producing things that look like arcs, but always subordinate and always being sandwiched between other stuff. So I don't think they're arcs. I think they're local tensional environments in very complex Archean accretionary origins that eventually fuse with the craton to form verticalized orogenic belts with a lot of late tonalite trondhjemite squirting up into it. A slightly younger crust forming process. There are earlier tonalite forming processes that are purely vertical. It has nothing to do with horizontal tectonics, and there are those that do. So both exist. Now, this sort of thing is not new. It's been proposed by a lot of people. This mafic accretionary prism and subcretion and slivering off. but it's always been interpreted in the context of a subduction-driven system, which creates a big problem. Because if this thing was being dragged down by a big, strong, stiff, coherent oceanic slab, why did it keep failing, right? If it was that strong and that dense, why did it shut down all the time, right? If it's stalling because of buoyancy, why was it going down in the first place? How does the next slice know it's supposed to throw itself under the wheels, right? Whereas if you interpret all of this as being craton driven, there's no subduction. The craton's drifting, and anything caught in front of it is in big trouble. It gets imbricated, the bottom drops off, and you form the characteristic Archaean accretionary origins this way. Very different from modern subduction margins in fundamental ways. The lower plate is completely passive. It's weak. It doesn't drive plate motion, right? You imbricate it, it melts over. There's no wedge. So there's nowhere to form these source-metasomatic arc magmas, which is why Archaean intermediate magmas are not arc magmas. The motion is slow because this resists motion, whereas there's no compression here. The slab falls off and the continent advances. Whereas here, it slows everything down. So this is probably why you don't have blue schists, in my opinion. Some modern orogenic systems do approach Archaean orogenic systems, and this happens when you get a buoyant bit. If you try to subduct an oceanic plateau that doesn't want to go down, well, you've got a problem. And the reason it works now is because continents drift independently of this oceanic system. They drift because of mantle traction. And so this is how you can basically overthrust buoyant oceanic plateaus and spreading ridges in a subduction system. In those cases, the melting happens deeper. It looks more like adachite, which look like GTGs, making this system much more Archaean-like than the normal subduction system. So we posit that the Western Superior actually records one of these Archaean accordion system where you have an overturn that partially disaggregates it, and then the flow pattern changed and the northern block drifted south and just recreated all these partially disaggregated terrains, one after the other, forming what I call the chaos style, the Kenoran accordion orogenic style. And I have to wonder how many Paleo-Proterozoic origins work this way. I think this is something that we need to look at. So I've been presenting this overall model. I'll now spend a fairly short time speculating on how this might have continued into the Proterozoic and how we can explain the beginning of plate tectonics. Before I do that, I'm just going to take a short step back to the Hadean. Obviously, the upper depleted mantle layer grew through time, right? Because you're constantly overturning and slowly consuming the primitive mantle layer at the expense of the depleted mantle layer. So the systematics are going to change with time. At the earliest stages, it's too different. It doesn't work anymore. You can't overturn because these depleted mantle layers that drove the earlier system, in part, are too thin. There's not enough leverage. So I'm not going to talk about this much. There's bombardments. There's all sorts of things. The Hadean system didn't work like the Archaean system. That's for sure. Moving forward in time to the latest Neo-Archaean, the 2.7 and 2.512 that ended the Archaean, you could argue that as these overturn upwelling zones move up, you're draining that layer. And eventually those bottom layers are going to be disconnected. This could maybe be tested with some numerical modeling like so many teams are doing now. And so the 2.7, well, we reworked the continents, a really big event, pushed stuff around. And around 2.5, well, things kind of locked up. So now I'm going to speculate shamelessly that the Siderean quiet period is in effect a pause. The mantle overturns slowly stopped, everything shut down, and you went into a stagnant lid phase. The big difference from the previous stagnant lid phases is due to secular cooling and the fact that continents generated in the Neo-Archaean were on average much more potassic They represent repeated remelting of older granitoids, TTGs. The potassium built up. All the radioactive elements were scavenged out of the bottom. And because of secular isotopic decay, these continental systems locked up around 2.5 and were then able to be eroded, dumping phosphorus and other essential components for life into the basin and form true passive margins for the first time with large sediment budgets. And ironstones. Adding phosphorus helped life get going, which generated oxygen, which generated the iron formations that typify this period. And then everything shut down and started again at 2.2. I would argue that the 2.2 to 1.8 period represents another mantle overturn stage. The system hadn't quite shut down yet. And you had a massive overturn pulse, but it was different from previous overturn pulses. Because one was smaller, the source was smaller, there was a lot less to feed these things. They weren't as hot because of secular cooling. But it was still enough to basically rupture every continent on Earth, creating these two, volcanic sequences of this age that are interbedded with rift deposits and so on, and kicking the whole system into motion again by rupturing the lid. The big difference from previous events is that when continents separated this time, well, the mantle temperature was lower. And so the new oceanic lithosphere that was formed there rapidly grew suboceanic lithospheric mantle roots that became very tough and focused deformation at the same place forever, as long as these blocks were diverging, forming spreading centers. As convergent margins, the far field ASOL was colder, stiffer, thicker. It was growing its lithospheric mantle too. So when subjected to compression at 2.2, it didn't behave like most Archaean oceanic lithosphere did in the past. It started to subduct and was tough enough to drag the slab behind it, forming the first subduction zones. So we get the first ridges and the first arcs. But not all ASOL are created equal. Some of the ASOL stayed buoyant and didn't want to go down and were weak and behaved much more like the Archaean convergent margins. Now I'm going to go very speculative and argue that the Proterozoic AMCGs record the progressive destruction of Archaean ASOL at Proterozoic convergent margins. So I'm going to address the Brontosaurus in the room here, the anorthosite, mangierite, charnockite, granite, gabbro sequence that everybody dances around because nobody can figure it out, right? They're focused in the Proterozoic. And there's basically two hypotheses. It's either an ephemeral source or a unique process. Now, these things are big. This shows their distribution in the superior craton. They basically compose 20% of the outcrop area, forming absolutely gigantic, multi-hundred kilometer thick body. This is from the name. See that mountain over on the horizon? Everything between here and there is composed of 95% plagioclase. How do you do that, right? Now, there's two models. There's the, basically the model where these are continental flood basalts, same old, same old. They form very thick underplates. And these are essentially feldspar cumulates. These very thick underplates dumped out the olivine and pyroxene, floated the feldspar. That went unstable to form these big feldspar-dominated diapirs. The granites are partial melts of the host rock in this interpretation. The question we have to ask ourselves is, why is this restricted to the Proterozoic? Proterozoic flood basalts don't really look very different from Phanerozoic flood basalts, so why now, right? And the prediction of this model is that these feldspar cumulates are precipitated out, are flotation cumulates from basalts of various types. And they're pretty garden variety basalts, right? There's no weird exotic basalts in the Proterozoic that could have yielded these anorthosite complexes. The competing model by Longhi, van der Alwera, and Jacques Duchesne involves crustal thickening. basically you thrust crustal rocks into the mantle, they heat up, they melt, and form yotunite, which is an iron-rich basalt that crystallizes the whole suite in tandem with anatectic biotite granite. So my test of this, apology for the geochemistry, is a whole rock trace element approach where I took the anorthosite and calculated the liquid that should have been in equilibrium with it based on whole rock data. I'm not going to go over all this methodology. For a single phase, this reduces to a very simple equation where the amount of trap melt is the only variable. And this is a typical rock profile for the Grenville anorthosite, and this is the model liquid. Okay? And I did this for a whole bunch of rocks. One year I had no budget. And thanks to the MRNQ for sending me the data, this is the Van N intrusion model solutions for typical anorthosites, typical messy anorthosites. Here's the final assemblage, lots of feldspar, a little bit of trap melt. It's the only, basically the only variable. You can do this for the vein anorthosites, you get the same result, basically. Fewer elements, this is older data, but basically a very steep normalized trace element profile. This is Morb. They do not look like basalts. They look just like Cenozoic adikites and closely resemble Archaean tonalites that are thought to form by melting of metabasalt in the presence of garnet. They have large positive strontium anomalies, large positive europium anomalies. They form by melting a basalt in the presence of garnet, basically, rutile-eclogite, probably, and are not basaltic. Going back to the Grenville anorthosite suite, this is the average low strontium P steep anorthosite suite model melt that I tried to match to forward melting models to see how, what source could probably give us this kind of signature. And it's often been posited that feldspar-rich cumulates are at the source of anorthosites. It makes a certain amount of sense. So I tried a bunch of melting models using arc cumulate sources, these open and gray symbols, and they all failed miserably because there's just not enough trace elements in there. On the other hand, I got some pretty good matches for a variety of arc-related basalts. Here's the green symbols are 30% melting of the typical Mount Misery low titanium basalt of Ordovician age in Newfoundland, right? Just typical depleted arc basalt. And it gives you a pretty darn good fit, right? So, looking at the whole Grenville anorthosite suite, not just the PSAS are these things. These are the melts computed to be in equilibrium with the anorthosites, whereas all the other symbols are all the other plutonic coeval facies, including the ferrogabbros. Ferrogabbros yield melts that look like tholiites, right? That iron-rich tholiites that fractionate that way. Whereas all the dominant mass of the anorthosites give you a trajectory that matches partial melting of typical arc-related basalt in the presence of garnet and rutile. So these are high-pressure basaltic melts, basically. That crystallize a lot of feldspar. And the blue things are things in between. They're mixes between these two stems. I just wanted to point out the position of the Bruno basalt in this diagram. This is the Archean basalt that we looked at from the Abitibi. They're not like the Mount Misery basalt. So at the time, I hadn't clued into this, so I was working within the framework of the Proterozoic paradigm. And I opted for the Duchesne model, but jazzed up with the Corrigan and Hanmer scenario of delaminating the slabs subsequent to crustal thickening. So you thicken our crust, you drop the bottom off of it, you upwell the mantle to bring in the heat, you melt that mantle, form a whole bunch of continental flood basalts that mix with large degree melting of island arc crust. Just want to back up here. Note that these things are at 60% melting, right? So if you're going to melt basalt to 60%, the feldspar is going to be of intermediate composition, which is why Proterozoic anorthosites have these huge masses of intermediate composition feldspar. They're high degree melts of metabasalt, whereas Archaean tonalites are up here. They're low degree melts of basalts. So what I did next is say, hey, maybe what's being consumed is an ephemeral source. Maybe it's that missing Archaean oceanic lithosphere that we want to get rid of. So here I directly compare the uncontaminated Archaean Bruno basalt to the Mount Misery basalt that was the source of all these partial melting trends in the previous diagram, and then they're basically the same, with a few exceptions, notably phosphorus, perhaps because phosphorus had not yet started being subducted into the mantle at that time. And the large ion lithophile elements. The Bruno is depleted compared to the Mount Misery, but Archaean terrains are not pure basalt. You know, they got 10 to 20% interbedded calc-alkaline rocks. So I just did a very simple back of the envelope, add 10% Archaean rhyodacite to this, and the mismatch is not really there anymore, right? If you consider an integrated Archaean greenstone sequence, it forms a very plausible protolith to the Proterozoic and Horstite suite. And so these two major problems would solve one another. So just to recap the whole story, bolides, the Archaean, the Hadean's different. When the bolides stopped and the upper depleted mantle layer had thickened enough, you went into a mantle overturn state with undepleted mantle welling up and yielding flood basalt sequences on the Archaean and Phanerozoic Earth. There were multiple pulses. They got bigger and bigger. The biggest one was in the Neo-Archean and essentially obliterated the previous record. There was probably a whole bunch of peaks and troughs here. If looking at the Northeast Superior, I think is the smoking gun here. Basically everything there is mass remelt of the older TTGs mixed with basalt. And these major overturns would drive episodic movement, accretionary orogenisis, Archaean style, and then things would shut down and go back into stagnant lid mode in between. The last big events in the Archaean, 27-ish and 25-ish, were a little different in that the crust was more buoyant and didn't quite behave the same way, but pretty much the same sort of thing. After 25, we lapsed into a stagnant lid phase that was very different from the previous ones, because now the continental crust was inherently emergent, because it was stiffer, because of secular isotopic decay. And the first passive margin sequences were deposited, the true ones were deposited in this phase. So this is an inter-overturn stage, and I would posit that all hell broke loose again around 2.2 due to a new overturn. So that ruptured the lid, kicked all the plates into motion once again, formed the first ridges, formed the first arcs. Question is, was the machine on? Did it stay on? Or did it need several kicks at the can to keep it going during the Proterozoic? I don't know enough about the Proterozoic to make that argument, but I think some of the audience might be able to. And so the question here is what happened to all the ASOL, right? At the end of the Archaean, 75% of the planet should have been covered with that stagnant lid crust that was very tough to subduct. And I would speculate that progressive consumption of the ASOL during the Proterozoic by subcretion and generation of AMCG complexes is a way to get rid of it, such that around 1 billion years ago, the last ASOL was destroyed and the Earth went into high gear. Everything accelerated and the modern plate tectonic system was born. Just to conclude, Bob was right. Thanks.
Thank you, John.
Okay, any questions?
Yeah, thanks a bunch, John. That was really a really great one to watch. We do have some questions for you already. The first one in here is a Paul Hoffman question. It reads, there is paleomagnetic evidence. Oh, so he sent this comment when you were first talking about your slide, when you said you're going to start speculating with the velocities of plates, plate motion. There's paleomagnetic evidence for plate velocity apparent polar wander back to Meso-Archean time. These data require either plate tectonics or true polar wander. if the scale of mantle convection was small, what would drive large, rapid, true polar wander on Archaean Earth?
Okay, a nested question. It's kind of hard to explain. I don't think that this style of continental drift was as efficient as modern continental drift because there's inherent resistance from the background oceanic lithosphere that doesn't have roots and doesn't tend to want to move. Now, during the very large overturn events, maybe the upper mantle got hot enough to allow fairly rapid motion of these continental blocks. I think as paleomag data improves, we'll be able to better constrain how Archean blocks move. But certainly during most of the Proterozoic, the motions were fairly slow with a marked speed up around 1 billion years ago. So this hypothesis, all this floating ASOL would gum up the works and slow down the whole system, but wouldn't necessarily prevent it from operating if the overturn was big enough. Now, there's no concrete evidence for seafloor spreading prior to 2.5. And the things that are older than 3.5 don't look like arcs to me. So I would argue that the plate tectonic system as we know it suddenly started around 2.2, and it took between 2.2 and 1 for all the ASOL to be liquidated, allowing the system to go into high gear. The ASOL would just gum up the works and slow everything down, but they wouldn't prevent these horizontal motions. They just slow everything down. Does that answer your question, Paul?
Interestingly, it looks like Paul is off the meeting. And I didn't notice until after I asked that question, but it's good that you answered it nonetheless. Our next question is from Catherine Bethan. It's either Bethany or Bethune. I'm sorry, I'm still piecing together people's names. She said, in the Ray Craton, there's evidence of large, disparate crustal blocks with unique histories juxtaposed against one another with arc-like magmatism along the boundaries, latest Neo-Proterozoic to early Paleoproterozoic. Is it fortuitous that magmatism due to overturning events came up along these boundaries?
No, not at all. I mean, the continent's going to rupture where it's weakest. If you have an ancient suture zone, that's a natural weak spot. And next time you impose extensional stress, or if you well up a big plume under it, that's where it's going to break. So I don't see that as inconsistent at all. With respect to the granitoids that are produced in the Paleoproterozoic, I think we need to take a serious look at them again. Some of them may be true art-related plutons, but some may not be. When you read the descriptions of a lot of Paleoproterozoic terrains, they really smell like Archean terrains, right? They're TTG, they're Shoshinitic things. They're the same as the Archean ones. So there may be a gray zone there. Does that answer your question, Kathy?
Yeah, I just would like to comment. Just I think I really respect your views and so on, but one frustration I have is that the Superior Province and in particular the Abitibi is not the only Archean terrain. And my concern is that the geologic records of Archean terrains, for example, the Slave Province has evidence of airfall deposits, so I think some of the generalizations that are made about, that are kind of based on the Abitibi geology need to be, you just need to potentially be careful. The second thing I'd like to say is that—
Can I address that one first?
Yeah, sure.
Before I forget what you said?
Yeah.
Okay, so the reason I focused on the Abitibi belt is because of the low overprinting deformation and metamorphism and its size. I mean, look at the size of this guy. So it's the only one that's really big enough that we can actually, put our foot down and say, this is what's happening. There are countless shreds of greenstone everywhere of various size. And what they usually do is they just take a little snippet of the Abitibi story in a very narrow time window, and usually at amphibolite grade. Everything I said about the Abitibi, I think, is directly applicable in general to most Archaean greenstones. It's pretty much representative. It's just that we see it so much better, and we can put our foot down because we have the context. And we see the older rocks, whereas most greenstone shreds, well, you're pissing in the wind because you don't know.
Yeah, well, actually, the Slave Province greenstone belts are relatively well preserved. The level of deformation is not that high. So.
I agree that the Slave is another very good example, but the Slave is a complicated place, as you know, and I didn't set up the deck for the Slave, but essentially everything I said would also apply to the Slave, I think.
Okay. So taking this a step further is, I just get concerned about, there's an archetypal Paleoproterozoic greenstone granite terrain. It's called the Reindeer Zone. And for those of you who are, I'm not a geochemist at all. I'm a field-orientated structural geologist, but I would point to the Reindeer Zone as a place for people to investigate, to look at the transition, because the geology of the Reindeer Zone is incredibly similar to the geology of the Slave, to an Archean terrain. And
How
yet
old is it again?
The Reindeer Zone is 1.9 to 1.8 billion years old. It's the collision between the Rayhern cratons and Superior Craton and the Sass Craton. It's
Can I try and address what you've said?
Yeah, sure.
Obviously, the Archean Proterozoic transition is not a line, right? There are things that look like post-Archean rocks that formed before, and there's things that look like Archean rocks that formed after. Because locally, rocks would behave in an Archean way, even though you're past 2.5. And as you approach the 2.5, well, the crust is getting thicker, you're getting more and more recycling. Things are slowly changing, but it's not like a totally step function, but pretty close to it. But it depends where you are. It's diachronous depending on the previous thermal history of whatever block you're examining. And there are Proterozoic blocks that act a lot like Archean blocks, and there's some late Archean blocks that sort of look like Proterozoic blocks, because each block had a distinct thermal history, depending on where it was relative to the upwelling zones.
Yeah, I guess I just say that there's a lot of big names in this audience in Precambrian geology, and I would point out to look to the Reindeer Zone because it's basically accepted to have been assembled by modern plate tectonic processes. Whether that's valid or not, I'm not sure, but it does have some of these transitional elements. For example, it has things that are ophiolite light, but not quite. And I think maybe that, yeah, sorry, I
heard that one before.
but I think there's a lot of literature available on the Reindeer Zone. It's been studied intensively, and there's lots of.
If you could send me a couple of the key, most recent ones, I'll gladly read it and give you my feedback. Obviously, the world didn't suddenly change at 2.5.
Yeah.
Right. There was a gradual transition of some kind, but the first convincing ophiolites and the first really convincing arcs are around 2.2.
Okay, fair enough.
All right, great, John. Next question is from Taras Jaria. He says, it looks like building craton terrains is the key to start the indenter tectonics. How do we form these terrains?
By structural and metamorphic facies analysis, I would say. But the analysis is only as good as the working hypothesis. if you assume that, for example, looking at this image, that all these terrains were originally linear terrains, well, you don't have a story. If you reinterpret the lateral variations of metamorphic grade in terms of where you are with respect to the indenture, you'll come up with a different story. For example, the Okinawa, which would be necked continental terrains with rift basins, would grade into the Ashuanipi, where it's much thicker and where essentially all the sediment gets migmatized, and you'd be closer to the margin of the continent in that sort of reconstruction. So it's a different way of thinking about it, in a sense.
No, John, what I mean is, in order to drive this indentar tectonics, you need kind of buoyant entity, which is rigid, which can squash the surrounding, right? So then my question is, how do we form this rigid entity with presumably depleted cratonic root and silicic crust, surrounded by more mafic material with thinner lithosphere or non-existing lithosphere and more mafic crust?
I think I'll shift to one of my cartoons just so I can wave my arms. Okay, so this is a good one. Okay, so
exactly. How do we form this bluish in the bottom and red on the top? Yeah, exactly. Yes.
This bit here. Okay, so the idea is that we know the age of subcontinental lithospheric mantle roots. They were first formed in the Archean because there's age data on the zircons from the xenoliths, and these things started growing in the Archean. In my interpretation, which is a minority view for the Phanerozoic, I think most Phanerozoic continents move because the background flow pattern is pushing against their mantle keels, and that process started in the Archean. Look at South America. There's no slab pull, and ridge push is not strong enough to create, the altiplano plateau. It has to be pushed by a mantle flow pattern at some point, and that started in the Archean, in my book. And because Archean cratons were so small, they naturally tended to form indentar structures. And we've just missed it because we haven't been thinking in those terms. We've been assuming big linear things. If we were looking at indentar tectonics, we could start looking at one side and then maybe spot the other side. But if you don't look for it, you don't see it. Does that answer your question?
Not really, because my question was rather, how do you form these indentars at the first place? What do you do to make them?
Okay, the indentars form because of repeated mantle overturns. The first time it comes up under Archaean-Style Oceanic Lithosphere, you might melt it and get 20% tonalite. Not quite common, but each time you underplate it by a mantle upwelling zone, you add more juvenile magma, which underplates, you remelt whatever was there, and passively enrich it in lithophile elements. So you go from tonalite to granodiorite to granite with time, but you're always remelting older tonalites. And in the 2006 paper, I posited that the cumulates and restites from that process, the eclogite, as it falls back into the depleted mantle, triggers a second generation of mantle melt generation. And so the keels under Archean continents grow down as a result of this backflow. And once they're formed, they're fragile. If the next ouzo comes underneath it, you'll kill it, but it will grow right back. And it's these things, these keels, that catch in the mantle wind and create the episodic Archean horizontal tectonics that are driven by the up and outflow of the ouzos. Is that a better answer?
Yes, thank you.
We aim to please.
All right, thanks. So for the next question from Jerome Van Hoon. Very nice talk, Sean. What causes these Archean? What causes these Archean overturns? Today, strong retreating old slabs typically lie flat in the transition zone, which leads to upper lower mantle separate convection. In the early Earth with weaker or no slabs, Earth might have had more whole mantle convection. Not sure how strong any overturns would be. Can you please elaborate a little?
Okay. I guess I forgot to emphasize that this is a hypothesis based principally on the geology, where I use the numerical experiments for mantle overturns as fodder to element the discussion, because I'm a field geologist, igneous petrologist, so I argue from what I understand. So now we know that the mantle is unlayered because the seismic show the slabs going all the way to the bottom. But we don't know that that was true in the Archean. We see repeated eruption of primitive mantle-like basalt coexisting with depleted mantle. There's different ways to structure that. I plunked for a two-layer model. It could be much more gradational than this. Not sure what, and there's a time lag. The upper mantle is cooling by exchanges with the hydrosphere. It hasn't got a large radioactive element budget, so there's no radioactive heating, whereas the lower mantle is heating up and becoming more buoyant. And at some stage, there will be some kind of an overturn event. Now, is there a dozen layers in between, or is it two big layers? I don't know. And as time goes on and we explore this hypothesis, well, maybe, it's a more shaded sort of thing. Maybe these oozos are intermittent at different places. Maybe they're planet-spanning events. Maybe there's a cascade of events. The actual morphology here was taken from reading stuff. I think we need a whole new generation of numerical simulations to tell us more about how these overturns actually occur, because I don't think we really know. I plucked this out of my head because it seems to explain the geological data. And I'm hoping that the modelers will tell me if I'm right or wrong downstream.
I wonder if it's, I mean, so basically it's the episodicity or the periodicity of these overturns. I mean, I agree that lower mantle will warm up, especially in the early Earth with lots of radiogenic heating. So they will have to go up to cool down again. And if you separate the upper and lower mantle, you're in trouble. So you need to exchange upper and lower mantle material. But the question is whether that happens continuously a little bit, or whether it just becomes in these huge bursts. And I think in the past, the idea was that these huge bursts are possible, and that was a model that Jeff Davies in the 19...
Yes, he was the first to suggest this.
Yeah, he suggested this, but since then we know that actually that phase transition at 660 kilometers is maybe not all that strong. It really only holds very cool slabs up, and only when they're retreating, whereas normal material probably will go through fairly easily. It's not that difficult to get it through. So I wonder if it's more like a continuous exchange, and in that case your model would still work, I guess. You would just
it depends on the time scale you're considering, Jerome. Viewed on the scale of the entire Archean, yeah, it's kind of gradational, but in practice it's pulsed. The Archean age distribution is very pulsed. Right? And when this process starts, the upper depleted layer would be quite thin, right? And as a fluid dynamician, you know that the ratio of thicknesses has a lot to do with the scale of the instabilities. If you have a very thin layer, you'll form little instabilities. Yeah. And so the shape and the scale of these downwelling and upwelling instabilities should have changed with time as the depleted upper mantle layer grew. By the time you get to the Paleo-Proterozoic, most of it was depleted mantle. And so I would argue that 2.2 event, which may be the last big upwelling, ruptured the lid and consumed most of that primitive mantle layer, leaving the unusually dense material in what we see now as LLSVPs, which would be the dregs of that lower layer that thinned through time and eventually disappeared somewhere in the Proterozoic.
Okay. Yeah. Well, and as you say, it probably needs to be looked at how episodic those overturns really
totally.
are.
I mean,
strong they are. Yeah.
There's a whole generation of models to be done based on this hypothesis. Now, in the Archean, the absence of the sub-oceanic lithospheric mantle means that anytime you have an oceanic slab forming, well, it's too small and buoyant, and it just doesn't go down. So you're lacking the process that created the OIB components, EM1, EM2, and high mu. They weren't being created yet because they're created by the slabs and material ponding at the core mantle boundary. And that wasn't happening yet because we don't find sodic series alkali basalts. We don't see that EM1, EM2 signature. You don't see the high mu signature. Okay? And numerical calculations by people like yourself show that Archaean-style oceanic lithosphere lacking a lithospheric mantle is just going to drip off.
Hmm. Yeah. Okay, yeah, great, thanks.
You're welcome. I look forward to getting more of your feedback in writing if there's other things you don't like about this.
It looks like discussion is continuing, but I myself need to go, so I'm going to pass it on to Andre. Andre,
Sure.
are you still here? Okay, thanks. Thanks, everyone. See you next week.
Okay, so we have one question from Srinivasan Bulusu. In the absence of plate tectonics,